Welcome again to Theory and Applications of Ground Vehicle Aerodynamics. In this session, we will look at the aerodynamics of trains. The aerodynamics of trains. Trains serve two primary purposes. They either transport passenger or they haul cargo. That's primarily what trains do. Move people or move goods. Sometimes both. Okay? But typically, the cargo train is different in design from the train that transports people. The boundary layer formed on a train is typically a turbulent boundary layer. This is true even when the speed is very slow. Because of the bluff body design that you have in the cargo train especially. So even at low speed, there is turbulence. So the flow around the train is typically a turbulent flow. When we looked at cars, we indicated that the primary structure that's being considered in the treatment of aerodynamic drag is the vehicle itself, whether it's a car or a truck or an SUV. In the case of trains, it's not that simple. There are three main contributors to drag. The three structures that contribute to aerodynamic drag are the subject train itself, the other train, that's another train passing by or going in the opposite direction to the subject train, and the tunnel. A lot of trains go through tunnels for an extended period of time, and these have contributions to the drag on the train. Let's look at the subject train. The subject train has the primary profile drag, and it has the intercoach interference drag also. Between the coaches, there is the drag just as you have in the drag between the tractor and the trailer. There is the drag between subsequent coaches, between the first and the second and the third all along. So that's the intercoach interference drag. There's the primary profile drag of the vehicle itself, the skin friction, and the pressure drag. And on top of that, there is the intercoach interference drag for the subject train. Now the other train, the train going in the opposite direction, and in fact, sometimes it's not common that you see one train going in the same direction as the other and just passing it. It happens, but it's not common in design and in operations of train. It's usually in the opposite direction. So typically, the other train is identified as a train or is described as a train that is going in the opposite direction. There's a contribution of that. And the reason that's important is the path of the other train is so close to the subject train that the air perturbation that the other train causes reaches readily to the subject train. The track is close to the subject train. There's only two train widths, about two train widths in general, between the subject train and the other train. Therefore, the subject train obviously is within the boundary layer of the other train. And of course, the tunnel that they go through. We will classify trains as passenger train, and we've already indicated before that they either carry passengers or they carry luggage. So when we look at the passenger train, there are three main forms. There's a citywide, which is generally low speed. Stops from stop to stop every few streets. The train stops, kind of like the trolley car. And we have the regional train, which has a high end of the low speed to medium speed, which is about 50 to 80 miles per hour. And the intercity commuter trains, that's where you have the Shinkansen train type of the maglev types of train. Those are the intercity commuter trains. And these days, intercontinental trains also. Those would be intercity commuter trains. They go from one country to the other. Okay, perhaps we should call them intracontinental, because I don't know yet. I don't think we have one train going from one continent to the other yet. But that may be coming at the speed at which trains are going these days. Well, the low-speed passenger trains pull about 6 to 10 cars, give or take a couple. That's generally the amount of cars that they pull. They make frequent stops. They're low speed. They generally are citywide, just like buses making stops at different places. They are sufficiently rounded to prevent blunts by the frontal face. This has some rounding in it, some kind of rounding at the edges. It's not like the square, blunt face that we have. This is your typical low-speed train, citywide train system. This is the typical one. They are sufficiently rounded to prevent blunt by the frontal face. It's the front that carries over 60% of the drag contribution, and so it's just the design of the front that's really dominant. After that, the back, the cars that they carry are essentially square boxes with a little modification on the top of them. Okay. It has the same car upper section design as the high-speed train, which is essentially a square box rounded at the corners and at the top with a little flaring at the top. And it has a high skin friction because because of its design. Generally, the skin friction is high, and the drag at the speed at which it's going is little. It's a high low speed condition of drag. If you recall from our treatment of airfoil earlier on, even at low speed you can have drag that is incurred highly. But, and also the design of the material is not intended necessarily to give it a smooth, polished teardrop body. So it's got high skin friction. High-speed trains are typically passenger trains pulling between 15 to 20 cars, and have speed, in some cases, exceeding 200 miles per hour. It becomes very high speed, and that's high speed, very high speed subsonic flow. Now, the high speed is great. It takes the passenger to where the passenger wants to get to right away. These are examples of high-speed trains. Only problem is there are challenges that accompany the high speed. With the high speed comes noise. Earlier on in the treatment of noise, you saw how the high speed causes an increase in noise because of the perturbation that is caused by the vibration of the air medium. So there's high speed in noise. There's greater noise. There's also a greater vibration of the structure itself. With the speed comes the increased vibration of the train itself. Okay. Impulse wave at exit tunnel, because the walls of the tunnel serve as boundaries to the wave that's generated from the high speed. They reflect back on the subsequent cars behind the front car, and they are a source of concern. They add pressure to the train. And also increase the vibration thereof. Then there is the passing of the opposite phased high-speed train on the adjacent tracks. So we have one high-speed train going this way. We have the other high-speed train going this way. Just this train on its own has its own problems. The noise, the vibration present and the impulse wave at the tunnel, even if it was the only train there. But you now have, in addition to that, the contribution from the other train that's passing. So, and these can cause a serious eardrum discomfort to passengers in the train. And remember, one of the things in vehicle design is passenger comfort. So these are the challenges: the noise, the vibration, the impulse wave at the tunnel exit, the passing of oppositely phased high-speed trains on adjacent tracks, and those tracks are about 2 train tracks apart. So they're about 2 train widths apart. So they're close enough to be of concern, and the eardrum discomfort to train passengers that comes from this. It's an example of what you have. This will be the tunnel walls. This is one wall of the tunnel. This is the center. Okay, so we've just drawn half the entire tunnel. The entire tunnel will be twice this width. So this is this train going this way. It's got a tunnel wall there. Now, as it goes, the air vibration that it causes hits this wall. So there's high pressure bouncing back on the train from here. Now, the wall on this side is way down here. Okay, it's the same distance from here to there, but on this side. So there's higher pressure here than would be coming from the wall there. So what happens is this pressure pushes this train. Well, the train doesn't get pushed, it's very heavy, but the effect of this pressure is to cause a lateral force against the train. As the train is going this way, there is a resultant lateral force in this direction. And as the train is following this turn, that lateral force causes a yawing moment around this point, around the tunnel center. So those are the effects as the train goes along. There's the vibration, there's the yawing moment that goes along with it, and that's just one of the trains. So one of the important things to consider in train design is to make effort to reduce the effect of lateral force. And that is the effect of yaw. The lateral force causes the yaw. And some of the things done to address that are the introduction of yaw damper between the cars to reduce the effect of damping moments. The introduction of semi-active suspension to reduce vibration by controlling damping coefficients. These are specific designs to address an aspect of the problem. Designing a long streamlined nose to reduce the lateral force itself. And once the lateral force is reduced, it means the pressure difference between the wall side and the center pressure is reduced. So the design of a long nose would help to reduce that. And this is being put into practice in the design of trains, actually, having longer noses and more aerodynamically profiled nose, so that there's good streamline coming, so that less of the force is being shot in the lateral direction, but it keeps going along the profile of the train, at least before the train starts to make a turn. Rounding of the bottom corners of the cars. Typical cars have square corners at the bottom, but rounding them off and kind of providing an aerodynamic leading edge to the bottom of the cars, they will help to reduce the lateral force, because then that force can just be sharing rather than impact force on the side of the train, on the side of the car, of the train car. And fins are sometimes included in the underbody of the train. There's a debate as to the effectiveness of the fins, but they haven't been found to cause any disadvantage. These measures they apply to train in an open environment, not just in the train track. They apply to trains in open environment. But if the train is in a curved path, as you were shown earlier, so the train is in a curved path as shown there. Okay, that's the train going along that curved path. curved path. If the train is in a curved path, concave to the wind, the tremendous weights, trains are very heavy, they're about 800,000 pounds, more than that, several tons of the train. The weight of the train combined with the fact that the center of rotation is now in the windward side. If it's concave, that means it's open to the wind from the center. That keeps the train stable against the pressure coming from the wall. And so it's relatively unaffected by the wind. But if the train is curved in the convex pattern to the wind, then the center of rotation is in the leeward side. The train will be subject to lateral force resulting in the yaw moment that is substantial. Worst case is when the train is in a straight path. The same wind pressure will generate a greater lateral force and a resulting greater yaw with vibration than with the train even in a convex path, because now there's no shearing off of the wind. It hits the train right on. So those are things, and you may not, a person may not have much control over that. The path that the train has to follow is the path that it has to follow. Sometimes the path is straight, sometimes it's convex, sometimes it's concave to the wind. There's no telling which direction the wind is coming from. So these are realities, but knowing those, at least one is aware of the kind of forces that they are subjected to as the train moves along. Freight trains. Well, freight trains, they're still, as they have been for ages, the workhorse of the industrial age. They haul over 50 cars and containers. In fact, they typically haul over 100, 120 cars these days. So they really are a workhorse. And they are very rugged. They last for a very long time. For a given engine horsepower, the more the cars, the lower is the train speed, certainly because it carries a higher load, and so its ability to move forward is reduced. Sometimes two locomotives are required to haul a freight train. If it's carrying a lot of heavy cartage, then an additional locomotive is provided to be able to move the luggage or the materials that are being carried. And usually there are different types of luggage that are carried. There's no, freight trains don't say, oh, I'm only carrying cars today, or I'm only carrying completed trucks or engines. Different types are put in different positions. There's no arrangement. And so it's really difficult to have a coincide aerodynamic profile for the cars following the engine in the freight train. It's hard to find freight trains exceeding 70 miles per hour, but at such speed, there isn't a lot of aerodynamic disadvantage that the train would suffer, even with its blunt nose. There's aerodynamic disadvantage, but it's not really substantial. And so not a lot of aerodynamic consideration is given to locomotive design for haulage. Even if aerodynamic consideration is taken into account there, remember we talked about cars. Once the speed starts to get to 55 miles per hour, we start to give it serious aerodynamic consideration in design. And train, they go at 40 and average about 40 miles per hour. But even at that speed, there's already drag present, and not a whole lot can probably be done, especially for haulage, for trains designed for haulage, just because of the form of the different devices that are present in it. Now, it's not impossible to give it an aerodynamic profile, but it probably may not be worth it in terms of the gain when you look at the materials that are being hauled and the lack of control by the aerodynamic profiling of those materials in the cars. So whatever gain has been may have been obtained by a redesign of the front section will probably almost be lost entirely by the time you get to the cars, maybe the 100th car down the road. But so it becomes a judgment call. But when we look at it, there is probably no optimization in having aerodynamic profile for freight trains. So we will leave this here. It's a little introduction to train, but hopefully it opens our minds or increases our interest in trains, which are ground vehicles with their own special roads, which are the train tracks. Thanks for watching.